Subscribe and press this bell icon to never miss another lecture video. Hi, welcome to GATE ESE Lecture. We are in lecture number 48 of Discrete-time system. We are in Discrete-time system, and here we are going to start our convolution or linear convolution in discrete-time domain. It is as similar as that of continuous time domain convolution, but there is a only difference is instead of using integration, we are going to use summation here. Simple. Now look here carefully, you can understand from the definition only. The discrete or linear convolution between two discrete time sequence x1n and x2n is defined as, okay, let me relate it with the continuous time domain, then you can understand. So you can take it like if there is x1t and x2t, the linear convolution which exists between, if you apply the convolution for x1t and x2t, the kind of value that you are going to get, you will get x1 tau, x2 t minus tau d tau, correct? The integration minus infinity to infinity. Similarly, here you are going to do x1, you need to first, we will go through this entire thing, change in index, then we're going to have a folding, then we're going to have shifting, then we're going to have a multiplication, but in the last stage, instead of integration, we're going to have a summation here. So if you follow this stages, so x3n equals to what? x1m into x2 n minus m, simple, ka summation n is equals to about whom that you are taking. Here we used to take tau value varies from minus infinity to infinity. So here my dummy variable is m for mango. M is dummy variable. So my m will vary minus infinity to infinity. Clear? It's as simple as that of continuous time convolution. If you have understood continuous time convolution, you can understand here. So my sincere request to you to go and have a crystal clear clarity on continuous time convolution, then you should come for the linear convolution in discrete time domain. Okay, now we are going to have the same procedure to evaluate the convolution for discrete time system. If you are having x1n and x2n, you need to do the change in index. So this will become x1m, x2m, just the way that we used to do x1 tau into x2 tau. Then and one second, and x2n and x2m. So first stage, what we did, we changed the index value. We changed from n to m, from naughty to mango. Okay, then we did the folding. Then we have to do the folding. How to do folding? You need to choose a value like as a second function so that you can do the folding. You can go for this one, you can go for this one. So I'm going to choose this one, x2m, as my second function. So x1 will going to lie like this, x1m will going to lie like this, and x2 minus m, I'm going to change here, x2n minus m, I'm sorry, x2 minus m, that is I folded the second function. Then we need to do the shifting here. x1m will going to lie there, then by shifting it will going to minus m plus n, or we can write down n minus m. So this is small m. Okay, my small m looks like a bit capital M, but this is a small m. Then you need to multiply these two terms. So here you need to write x1m into x2n minus m. Till now we are following the same pattern as that of change in index, folding, shifting, multiplication, as that of continuous time signal. But in the last stage, instead of doing integration, here we are going to do summation, and we need to vary the values of m from m is equal to minus infinity to infinity. Clear this concept? Okay, now moving on to our simple concepts. Yes, your linear convolution obeys commutative property. Yes, it obeys associative property, and yes, it obeys distributive properties as well. Okay, distributive property as well. Simple hai, clear hai? Is there any problem here? This is the same concept. I'm not going to repeat all these concepts again. You understand it? Okay, it's the same concept if your two discrete time systems which is having impulse response h1n and h2n are connected in cascaded manner, then then these two discrete time systems can be replaced by a single discrete time system having the impulse response, which is nothing but the convolution of these two impulse response. Okay, that is h1n convolution h2n. The same way, if we are having a parallel connection like this, so it can be replaced by the summation of these two impulse responses. So it's the same condition. Now let's solve a simple question here. It's given key the impulse response, that is 1 by 2 to the power n into un, 1 by 4 to the power n into un. These two are impulse response of these two different discrete time systems, and what is the equivalent. So if you are going to replace it, it's a very simple thing here. If you want to replace it by equivalent model, that is so if the impulse response of this one is h1n and this is your h2n, then the equivalent impulse response with which it get replaced, so that equivalent impulse response will be nothing but h1n convolution h2n. Now I'm going to calculate the h1n and h2n value. So putting the formula h1m into h2n minus m, simple thing. Now here in this analysis, we mostly going to use this will going to be your useful formula for all of this kind of analysis in convolution, basically discrete time domain convolution. So you're going to use this explicitly. Also you're going to use the infinity sum formula. You know these formulas. Yes, I have told you in signal system, discrete time system. I'm not going to write it down again and again. Look here carefully. So as we are going to have h1m here, my h1m is nothing but 1 by 2 to the power n, so that n will be replaced by m into u of m, yes, into h2n minus m, that is 1 by 4 n minus m into u of n minus m. Clear? So summation m is equals to minus infinity to infinity. So we have this um and we have this n minus m. After the removal of these two parties exactly is that of continuous time domain. So this limit will be changed from m equals to 0 to n. Yes or no? We used to do na u of t, u of tau, and u of t minus tau. Yes, this will lead for the 0 to t, 0 to infinity, and t minus tau removes this 0 to t. Clear? We have understood this. We have done the analysis, lot of analysis here on this concept, so I'm not going to repeat that concept again. So now we are going to have a new limit, that is m equals to 0 to n, 1 by 2 to the power m, 1 by 4 to the power n, and 1 by 4 to the power minus m. I just separated these two terms. Now 1 by 4 to the power minus m can also be written as 4 to the power m. Yes or no? Will that be any problem? No. Now 4 to the power m, you can put this entire term over here, so this can be written as 4 by 2 to the power m. 4 by 2 to the power m is nothing but 2 to the power m. Yes or no? So this came out to be 1 by 4 to the power n into 2 to the power Clear? This will be your answer. This will going to be your answer into un for all. So I multiplied a un in order to replace this for n greater than equals to 0 condition. Okay, moving on. Convolution in discrete time domain is actually the syllabus includes your linear convolution, circular convolution, and section convolution in discrete time domain, right? Now your circular convolution and section convolution, your section convolution is also divided into two ways, that is overlap add method and overlap save method. Okay, now these two category, this category and this category is absolutely important. It is having a lot of importance for your semester exam. This is having also some, it might have some importance for your semester exams, but for GATE and engineering service I'm going for this only, this much only. I'm not going to include all of these things. I'm not going to make you study the circular convolution. I'm not going to make you study the section convolution, graphical convolution, tabular convolution. There are so many concepts, so many ideas for GATE exams. I need to discuss a lot of questions. I'm going on the basic level right now, so it's going to kill a lot of times. And I want to prepare you for GATE exams, engineering service exam, public sector exam. For that, this is the only part which is important. These parts are not important at all. So do not waste your time reading and studying and understanding all these concepts. Okay, in the next video lecture, I'm going to discuss this part only, this part only, this part only. Okay, thank you so much for watching this video lecture. See you in the next video lecture. Till then, bye.